Hello student, I am Dr. Hisam, your subject teacher. In previous class we discussed about the integration, and in this integration we have developed quadrature. So from the quadrature let we start. So this is the quadrature, and this quadrature was developed through the integration process. And in through this quadrature, we can easily derive any integral formulas to integrate any type of function. So that first of all, we discuss the trapezoidal rule. Basically, so many rules are there, so many methods are there. First of all, we prove that the trapezoidal rule. So in that quadrature, this trapezoidal rule is a basic formula and valid for linear function. So because any integral function is given and function must be linear. After linear, this formula is also valid. You can easily integrate any function through this trapezoidal rule. But limitation is a linear. So if we put n is equal to 1 because of the linear in quadrature, and taking some curve, the whole curve is given, n points are given. So let we choose any two points, x0, y0, and x1, y1 as a straight line. So because of the 2 points and the line is straight and n is equal to 1, so no need of higher differences, so that higher differences become 0 in quadrature. So in quadrature, when we put n is equal to 1 and higher differences means more than 1, only terms is n y naught, n square upon 2 delta y naught, and this is the square term, this is the cube term, and fourth term and fifth term, all are omitted, all are cancelled. After that, when n is equal to 1 in quadrature, let we see that n is equal to 1, the term is y naught, and 1 upon 2 delta y naught, so remaining term and h remains same, y naught 1 upon 2 delta y naught. First of all, we take the 2 points, so the integral is x naught to x naught plus h, x naught plus h means this is x1 means the first 2 points x naught to x1, f of x dx same, and n is equal to 1 in here. After LCM, h, this is the 2y naught delta y naught upon 2. And when we remove delta, according to definition of delta, it's the difference of the delta y naught and the difference of the y1 minus y naught. And there's a 2y naught minus y naught, the remaining term y naught plus y1 and the h upon 2. When we integrate f of x in between x naught to x1, the result became as h upon 2 y naught plus y1 on x naught to x1. Similarly, when we change these points x1, y1 and x2, y2, so integral will be x naught plus h means this is x1, x naught plus 2h, this is x2, f of x dx, n is equal to 1. And here in place of y naught, where we put y1 because the initial point is x1. So here the y1 plus 1 upon 2 delta y1. Same after LCM and the definition of delta y1, this is y2 minus 1, that will be there. After simplification, when we integrate f of x dx in between x1 to x2, the result will be h upon 2 y1 plus y2. If you see these both h upon 2 and both same, and when we integrate f of x in between x naught to x1, the result will be y naught plus y1. And here when we integrate 1 to 2, the result will be 1 to 2. Similarly, when we integrate f of x on another 2 points, x2 to x3, the result will be h upon 2 same y2 plus y3. Similarly, when we integrate f of x in between any 2 points, say suppose n minus 1 to nth value, x naught plus nh, this is the b, this is the last limit. And in between these 2 points, the result will be h upon 2 yn minus 1 plus yn. Actually, we need one integration x naught plus nh. This is our whole integration. We integrate this function generally. But here in trapezoidal rule and here we integrate piecewise, point to point. So for collection, when we combine all sub-integrals in our whole integral, so the process is above all integral we get, this is the left hand side and this is the right hand side. So in left hand side, if you see that upper limit in first integral and lower limit in second integral is same. So when we put upper limit and lower limit, you see that the signs will be opposite because upper limit put directly and lower limit put negative first, then put. So plus minus will be cancelled. This is x2 and this is x2, this is x3 and the next will be x3 and the last one. If you see in the left hand side, only lower limit x naught that is equal to a and x naught plus nh that is equal to b, only remaining these two integral and remaining all terms are cancelled. And also there is a property of sub-integrals. The remaining integration will be, remaining limits in integration will be x naught to x naught plus nh. And right hand side, h upon 2, you see that h upon 2 will be common and the aid all terms. Next slide. So in left hand side, apply the property of integral, that the integral is subdivided into n subintegrals. This is the property, so that remaining integration f of x ds in between x naught to x naught plus nh and right hand side h upon 2, and these are the values of the y, that these are called the entry. So in right hand side we see that except the first and last entry, means first means y naught and last entry means yn, all entry other than first entry and last entry, all entries are doubled or twice, y1 y1, y2 y2 and similarly. So when we combine all h upon 2 same, y naught plus yn as a common plus twice y1 to yn minus 1. So this is the formula of the trapezoidal rule. When we put n is equal to 1, we can integrate easily. Mostly this formula is suitable for the polynomial function of first order only, means only linear. This is the trapezoidal rule. And also so many methods are there: Simpson's 1/3 rule, Simpson's 3/8 rule, and Weddell's rule. So this is our quadrature. In quadrature, when we put n is equal to 1 and neglect all higher terms, we can easily derive trapezoidal rule. When we put n is equal to 2 up to here and all terms are neglected, 0, count as 0, we can easily prove the Simpson 1/3 rule. And Simpson 3/8 rule, n is equal to 3, and similarly n is equal to 6, we can easily derive the Weddell's rule. So this is the integration formula, trapezoidal rule, and other so many methods are available. Thank you very much.